Thank you very much. Thank you for the introduction and the very welcome invitation to this One World seminar. I'm honored to be here, a little worried because if I say something more exotic, it's hard to tell from the faces of the audience if I have to stop or to change pace. So what I'm going to talk about is some gamma convergence applications to large data, say, if you want. And in particular to continuum limits of where you have some kind of interfacial energies arising on graphs. So the type of problem we have in mind is the typical problem of calculus of variation. So we have a set, and we have to subdivide the set into subsets, maybe two subsets, so that some energy is minimized. And we think of this as an interfacial energies between the two sets. So it's the starting problem of calculus of variation, DDoS problems. But now we have a different setting. So we have a graph. So instead of having a region of the plane or the space, we have a graph, which is a set of vertices and a set of edges. So not all points are connected in the graphs, but we have a set of edges. And the idea is to minimize some energies defined on edges. The easiest energy is just the number of edges. So the picture we have in mind, we picture our graph into colors, and we minimize the number of edges of the graph which connect points with different colors. As the number of nodes of the graph diverges, then we want to keep trace of what happens to these kind of problems and see what is the limit behavior. So the plan of the seminar is the following. So first, we embed these kind of problems in a variational setting, and we talk about gamma convergence very briefly. Then we will see what happens for some class of lattice energies. So when the graphs are parts of a lattice, and in particular when they are sparse. So we embed the lattice in some lattice. We embed the graph in some lattice of some dimension, and we suppose that the number of edges is much smaller than the total possible number of bonds, so pairs of the lattice. Then we will see that we have a description in this case, but somehow we see the arising of some issues due to topology. And there will be a short intermission where we will see what kind of problem arise also for very simple sparse graphs. And then we will go to dense graphs. So when the number of edges is of the same order of the total number of possible bonds. So what is variational analysis? So we transform our our problem, which is defined on sets, in problem defined on functions. So we introduce a parameter, a parameter which is which labels the families we want to take into account. So the easiest case is when you have two families. So we will stick to this case, and also because in this two parameter setting, we can choose the parameter very symmetric, being 1 and -1. So a subdivision or subset, say, or of the subsets of the graph are function defined on the graph with values -1, 1. If you are one family, you value 1, the other -1, which are called spin functions. We don't impose any cardinality on the number of nodes of vertices in which you take value 1 or -1, because this can be imposed a posteriori. Then we define the edge energies in terms of these spin functions. And this is a way to define them. So to every edge, we associate a number, positive or non-negative number, Aij, which is the strength of the edges, of the edge. And if you are not in the set of edges, then we set Aij equal to 0. So the energy can be written as a sum of all pairs of vertices. And we have a normalization factor because here ui minus uj is equal to 0 or 2 in modulus. So in the case when Aij are equal to 1 on the edges, this is just the number of edges. So this is another way to write the same thing. And then we want to pass the limit and see what happens to the minimal cut problems. But this is done by defining a limit energy, not looking at the problem themselves, not looking at the solutions, but looking at the behavior of the energies. And to define a limit energy, which is gamma limit, and in such a way that this gives, so the minimal cut problems for the limit are approximate minimal cut problems for the converging graph or the diverging graphs. It's important here to have some compactness properties of minimizing sequence that suggest which is the limit energy. And this is different in the case of sparse or dense graphs. So we start with what has been done in the last 20 years, say, and a lot of work has been done in connection with image segmentation and fracture mechanics, and some more recently on data science. When you consider lattice graphs, and in this case, the model we have in mind is very simple and apparently has nothing to do with our problem. So the model is the Ising system. So the graph here is ZD. So we start with a very nice environment, very regular environment, a square lattice in the dimension. Or maybe it's better to think of having a portion of this lattice. So the portion which is contained in the bounded domain. And the set of edges are just the nearest neighbors. So here is a representation. The edges are just these lines here. And so now the parameter is defined on ZD, and this is the energy. So the energy now is just a sum on nearest neighbors. So the idea here is to identify each spin function again with a set. And this set is very regular. It's a union of squares. So we identify each function u with the set where u is equal 1. These black nodes say. To every black vertex, we associate the square with unit square centered in the vertex, and then you make the union of the square. Now we see that this energy is just the perimeter of this set. So we have a natural environment in which you have a compactness property, because we know that we have from geometric measure theory that the class of sets of finite perimeter is pre-compact on sets with equibounded perimeter. So it's not necessary to know the fine properties of sets of finite perimeter, just regard them as sets with C1 boundary. And in our notation, we will denote by HD-1, the D-1 dimensional Hausdorff equation, which is just the surface measure on the boundary of these sets. So now instead of having directly the number of nodes diverging, we introduce a small parameter and scale the graph. So now the graph is just a scaled version of ZD. And if you want, the local version is when you intersect this scalar ZD with the same fixed set D domain D, so that the number of vertices diverges like epsilon to the minus D. And the important thing here is that we can define a scale version of the energy by multiplying by a scaling factor, which is the surface scaling factor. With this, this energy is the same as before, just multiplied by a constant, but this constant gives that we have still the interpretation of the energy as a perimeter of the set, which is the union of the epsilon cubes centered in the nodes where U is equal to 1. And so we have, we can embed our convergence, our functions into sets of finite perimeter, and we can say that our spin function tends to a set if the corresponding set of finite perimeter tends to some A, and use the machinery that also was first developed by myself and Ambrosio a long time ago, say, to describe the limit as an integral on the boundary of the set. So this integral retains some features of the asymmetry of the lattice in this very simple case. And if you want, this just reads that minimal cut problems for these on these graphs converge to the minimal cut problem, say, with respect to this. So least perimeter problems with respect to this perimeter. Okay, well, how general is this approach? Well, as long as we stay on ZD, we have used just the compactness of the sets and some machinery, which is developed in the continuum, essentially, and we have transposed it on the discrete. So as long as we remain in this kind of setting, we can enlarge the graphs by taking not just the vertices of epsilon ZD with nearest neighbors, but also with edges that connect other bonds. So every ij can be in principle every I can be in principle connected to an edge to any j, but this strength of the connection of the edges must decay as a minus j, as the distance between these vertices goes to infinity. And in this case, we have a limit which is can be also non-homogeneous depending on x. But if it is homogeneous, this is just a convex function of the normal. And one thing is that we have to understand here that can be of use is that if we take into account more and more neighbors of a set, even keeping the ZD environment, we can get more and more symmetric limit functions. And this can be used, for example, in image reconstruction, for example, to have in the limit some isotropic energy, which is important in applications. For example, if you take the nearest neighbors in 2D, we have seen we have a square symmetry, but if you take next to nearest neighbors, we have an octagonal symmetry, and somehow you get more and more symmetric phi in the limit. But anyhow, you get some kind of perimeter in the limit. Well, the ZD is not very important. You can have any Bravais lattice or even multilattice, and also some aperiodic lattice like Penrose tilings and so on, or even randomly chosen subsets of ZD. So you can have you can choose with an IID random variable set in ZD as long as you have sufficiently high probability of having points chosen. And this is, again, a good lattice where to define a limit perimeter. You can also have some dynamical problem treated, but that's another story. Or you can have more than 2 parameters. And then in the limit, you get an optimal partition, not just an optimal interface problem. Now, this is very nice, but still we are on a lattice environment. How can we try to exit from this environment? Well, one way is to not require to have a lattice, but something which, when coarse-grained, behaves like a lattice. Now, I've been not very precise in this slide, but somehow you can have a disordered set. And as long as you have some scales, so epsilon, I called epsilon and R epsilon. Well, epsilon is the average distance between points, say, and so that you have some distance that goes to 0, so it is scaled to something on converging on a continuum. But then we have a larger scale, R epsilon. Well, here I have not mentioned it, but epsilon times R epsilon must be still small, and these scales must be such that when you average, when you compute, say, the number of points in an average square of side length epsilon r, this behaving of the order of epsilon r to the d. So the type of density that you expect, and still you have some interaction between neighboring cubes. So somehow that essentially that the interaction behave like epsilon to the R epsilon. Okay. Then we still have a compactness result by using a coarse-grained variable. So you take covering of your space into cubes of size epsilon R epsilon. To each of these cubes, you associate, you associate the variable 1 if all the nodes have, of the spin function that you take into account has a value 1, and if you take the value -1 otherwise. So this seems arbitrary because you can have also points in which cubes, say, in which you have both values, but these are negligible. And so you can start again this compactness results. And this is, I like to mention, it's very reminiscent of something that Nicolas Garcia-Trillas and Slepchev have used to coarse-grain some problems in which the total variation appears. There, the lattice is generated by some random variable. Okay, this is a way, so coarse-graining. Recently, with Andrei Patnitsky, we have also used some percolation arguments, in which the difference is we don't coarse-grain in the energy, but somehow we use some coarse-grain geometric features of the lattice. So this is the case of Poisson random sets. So the graph, the vertices of the graphs are given by a Poisson cloud. So Poisson random set with some intensity lambda, and which is just a set of points distributed according to this law in Rn, Rd. Actually, we are looking only at the case t equals 2 for some technical reason that maybe I will talk about afterwards. So these are uniformly distributed points with this law, and the edges of this graph are given by nearest neighbors. Nearest neighbors are defined through Voronoi cells. So every point of the lattice has a cell which is defined as the points which are closer to this point than to the other points of the lattice. So this is a convex polytope, and well, a convex polygon, polyhedron, say, or in R2. And we say the 2 points are nearest neighbors if their Voronoi cells have a common edge. So these are 2 neighboring points, and this is the common edge of the Voronoi cells. And then the graph is what is called the Delaunay triangulation of the lattice. So in which you, as edges, you have the bonds connected near neighbors. So this is not what before was described as a regular set, because the idea of a regular set is that you don't have large holes and you don't have accumulation of points. Now we can have points of this set arbitrarily close, and you can have cubes of arbitrary size in which you don't have points of this set. So this is a drawback, but on the other hand, this set is isotropic. So because the properties of the Poisson random sets are invariant under rotations and translations. So this is an isotropic set, an isotropic environment, say. So how can we export this discrete-to-continuum approach where the ferromagnetic energy, the Ising energy, is defined as the same way, where here now the sum is between nearest neighbors, and we scale it with the same scaling. But now it's not clear that this is a surface scaling a priori, because well, because we still can associate to each function, to each fixed function, the union of the Voronoi cells where u is equal to 1, and scale them. But the union of this Voronoi cell gives a set of which the perimeter is not estimated by this function. So a priori, we don't know that this immediately, at least, that if this function this energy is finite on some function, then we have an estimate of the perimeter in terms of the energy. Because we have, even for a single Voronoi cell, we can have large cells with few edges or small cell with many edges, and this counts the edges. But we have we have proved the lemma with Piatnitsky that states that, okay, the set, we cannot estimate the set in terms of the energy, but we can remove some part of the set, this red part, or add some part to this set, and this part that we add and we remove are negligible, such that we can create what remains, so that here now is the region enclosed by this light blue curve. So this region is a set of finite perimeter. So still we have a compactness of this family. So it's not directly, the perimeter is not directly dominated, but up to removing small sets, it is. So we can start this gamma convergence process. Now there is a technical part because it's not sufficient to have compactness of the sets. You have to have some control also on the behavior of the energy, which is a kind of geometric control, which was in the case of ZD is given by the fact that ZD has a nice geometry, and in this regularity of the geometry can be achieved by considering a subset of the Voronoi cells. The subset of the Voronoi cells which are neither too big nor too small. So we impose that they are larger, they contain a ball of some radius, and they are not larger than 1 over the same constant alpha here, and we control the number of edges. And we have proven a geometric property of this set, which says that this set behaves like ZD in a sense, in a rather technical way. So the way we have stated this is that okay, we can find a length scale, say, which is independent of epsilon, if you want, depends on alpha, such that if you take large cubes here on the original Poisson sets, and then you take the covering of Z2 by these squares and cubes, then the cubes which are connected, whose center are connected with Voronoi cells belonging to this class, then these follow the Bernoulli-Pont percolation theory. So the probability of having connected cubes is larger than some positive probability into dimension larger than 1/2, and this is enough to apply the Bernoulli-Pont percolation theory. So somehow this gives a sublattice which has good geometric property, and this allows to start the computation of the limit. So it's not important how you define the limit, but the important thing is that it is isotropic. So the limit perimeter is indeed the length of the boundary of the set times a constant, which is an absolute constant, times the square root of the intensity of the Poisson random set. So somehow here, the isotropy of the limit is obtained through the isotropy of the Poisson random set and not as a regularizing effect of long-range interactions like in the coarse-graining case. So this is a whole set of examples which show concentration of the energy on interfaces. Somehow the one hint, one conjecture could be that if in this scaled environment, the interactions are at the vanishing scale. So in this setting was epsilon times R epsilon that was going to 0, then the limit is an interface. Unfortunately, this is not the case. And we have a very simple one-dimensional example. So it's simple in the statement, and then there is some difficulty in the proofs, which is as follows. So in 1D, everything is very clear. You expect for minimal partition problems to have one interface somewhere, and this interface is due to this Ising system. Maybe this interface is spread out, meaning that in the computation of the interface, a lot of neighbors intervene if you have a longer range. But we have an example in which you have interaction between nearest neighbors and 1 over square root of epsilon neighbors. Recall that epsilon going to 0. So in the lattice, in the scaled lattice, you have this is the epsilon neighbor, and this is the square root of epsilon neighbor. So the interaction then converges. The range of interaction does converge to 0. But we have seen that together with Andrea Braides and Margherita Solci, we have seen that the behavior of the minimal cut problem does not give a sharp interface, but instead a diffuse interface. And these are examples in which you prescribe microscopically, say, the number of points which are in one of these phases. This is the microscopic picture, say, which repeats in a sense regularly in the sample. And so you see a behavior in which some interfaces, some sharp interfaces, are generated at a small scale, but then they are homogenized. And in the limit, since we mix ones and -1, the limit is not a sharp interface limit. So it's, you lose the constraint u equals to 1. Okay, so there is something that we have to trace of topological, topological origin. So in this case, why it's topological origin? Because the idea is of this example is that this looks like a one-dimensional example, but instead is the projection of a two-dimensional nearest neighbor interaction Ising system on one dimension. So we come to the final part, which is the treatment of dense graphs. So we still have the same type of terminology. So we have a graph, which is now an abstract graph. It's not embedded in any RD, and with vertices and edges. And we have, we call n, little n, the number of vertices of G. So the G is, can be parameterized on 1 over n. So we leave the ZD or the d-dimensional parameterization, and we go to one-dimensional parameterization. Since we don't have any structure, then it's we take the simplest parameterization that we have. And the energy, which is still of the form that we have seen before, is described by the adjacency matrix, which we take the simplest one. So we are just counting the number of edges that are separated in this choice of the spin function here. So Aij is either 1 or 0. So here it's an example of a graph, and here it's the corresponding matrix. And so we would like to see, as we increase, we have a sequence of graphs maybe of with increasing small n, what happens to the limit. Well, we don't want to see it. There is a theory that tells us what is the way to describe the limit object. And the idea is now to look at the convergence which maintains the topological characteristic of graphs. While for lattice, we were happy to have a common environment, and the topology was somehow given by the environment. And here, or the dimensions, say, of the environment, here we have to look what is the behavior of the topology. And the way this has been done, I refer to Lovatz and other, I'm not an expert of this matter, is to look at what is called the homomorphism densities of a given graph inside another graph. So we take more or less the number of copies of a given graph inside the graph G. And if we have a sequence, then we can look at how given f this quantity behaves. This is called the left convergence. So we say that the sequence of graphs Gn is left convergence if every time you fix a simple graph, so we have a test graph, which is simple, then the quantities converge. Okay. And this is a type of convergence which is meaningless if we have sparse graphs, because for sparse graphs, for every fixed f, these all converge to 0. But what is the limit? How can we describe the limit? So the idea of Lovatz and others is to embed this graph setting in a functional setting and define a functional version, which is very close to a weak convergence of left convergence. So if we have a finite graph, to every finite graph, we can associate a piecewise constant matrix, piecewise constant function, sorry, which is essentially obtained by taking the value 1 on a square corresponding where the adjacency matrix is 1, and you take value 0. You take the value 0 elsewhere. So you extend this matrix from 1 over n z, a portion of 1 over n z2 to the square 0, 1 times 0, 1. So here in the previous example was the adjacency matrix, and this is the interpolation. And the idea of a graphon is just to extend this definition when we don't impose this to be piecewise constant on square of size 1 over n. So a graphon is just a symmetric bounded measurable function which is defined on 0, 1 times 0, 1. There is a little difficulty in the visualization here, because for matrices 0, 0 is on the top left corner, while if you regard 0, 1, 0, 1 in the usual Cartesian representation, the 0, 0 is on the bottom left corner. So sometimes there is a difficulty in visualization of the graphons. So here is a heuristical description. So a graphon is a graph with 0, 1 as the set of vertices. So we have a continuum of vertices, and this is the adjacency matrix is given by this function here. So here are other examples. If you have a complete graph, so every point is connected with all other points, the W is just identically 1. Here we have weakly connected subgraphs. So we have on the diagonal here squares. So we have 1 where everything is connected with everything. Here is a bipartite graph and half graph that are pictured here. I hope you can see them. And you also have fancy real life examples with large networks like the ones are pictured here. And I took from a paper by Karen and Fox of 2017. And so you can picture some of the characteristic of the adjacency matrix also in these simple examples in these real life large networks. So how to define, we have defined the convergence, but this is a topological object, and we would like to have this connected to some functional analytic concept. And the first thing that has been done is to define a norm defined on graphons. And this norm is a kind of weak L1 norm. So if we have a sequence of W's here and you test them with the L infinity function, this is the definition of the pointwise convergence of this quantity here is the convergent definition of weak L1 convergence, and then you have the supremum over all functions. So it's a kind of uniform weak L1 norm. But the drawback of this, so this defines a convergence of graphons, but the drawback is that it depends on the parameterization. So there is not a single way to parameterize a graphon. You can shuffle, say, the numbering of the nodes, and you take another graphon with this which is of positive distance in this case, in this norm. And so these are two different parameterization of a bipartite graph. And here we concentrate the nodes with connections on the two halves of 0, 1, while here we mix them. So here we see this one is converging, so it's constant actually. While here, as n increases, this converges weakly. This converges weakly to 1/2, to the constant 1/2, and in part, and we see that it does not converge in the cut norm to its weak limit. So we have we lack compactness. This compactness is achieved by using a cut distance, where we infinize the cut norm with respect to rearrangements. So in this way, the distance, the cut distance between two different rearrangements of the same graphon, of the same graph, is 0, of course. And the important result that you find in the literature is that the convergence in the cut norm, in the cut metric, in the cut distance, is equivalent to left convergence. And you can define a limit, and in this limit you can define some quantity which is the graphon version of the homeomorphism densities. So you can define a limit of sequence of graphs, and this is coherent with the requirement that topological quantities converge. The important thing is the compactness. This is a compact convergence, and there is always a relabeling of the vertices such that once you have a limit, then you can relabel the graphs so that they converge in the cut metric, which is more which is easier to handle. Okay, so our little contribution arrives at this point where we have a few minutes to conclude. So we can take our energies defined on graphs. Now we have to rescale them, and the scaling now is not a surface scaling, but is a bulk scaling. If you want, we divide by the total number of all possible bonds, or something proportional to it. Okay, so this is the number of the proportion of the bonds. Of the vertices, and so n square is proportional to the number of all possible bonds, and we compute this limit essentially with respect to the L-infinity weak star convergence. So in this case, we have spin functions are defined on say 1 over this n and z, and are interpolated piecewise constant, and we look at the convergence of this energy with respect to the weak star convergence, L-infinity weak star convergence of spin functions. Now we lose the constraint that the spin function remains spin function in the limit, but we have a precise representation in terms of the limit graphon. So this theorem says that, okay, we can define a limit of graphs, of dense graphs, as the number of nodes goes to infinity. This limit, up to relabeling, we can think that it is a limit in the cut norm. The limit is a graphon, so it's a function defined on 0, 1 to 0, 1. And the limit energy is this kind of double integral, so it's a non-local energy with W as a coefficient, and then you have something which depends on the limit function. But the limit functions now, they don't take just the value 1 or -1, but they take all the values between -1 and 1. So the limit energy does not have a sharp interface, but the U must be understood as a density of one of the two phases, and you have an energy which mixes the phases at the microscopic level. And the important thing is that this convergence is compatible with the integral constraint, which is the way you express the constraint on the number of nodes that are in one of the two families, 1 minus 1, so that you obtain an approximate cut problem. Hopefully, since there is a lot of work on non-local functionals here, there are ways to explicitly construct solution to minimal cut problem in the limit. There is a proof, which I don't want to show, but I see that I want to show you that this is a relatively easy proof, meaning that all the work here is just to prove that the kind of convergence that you have on graphon implies a very strong convergence, which implies gamma convergence. It's a kind of continuous convergence of the energies, even though they are defined on different spaces. Okay. And the difficult part here, the unknown part here, is really how to compute this W. While in the case of the interfaces, we have a machinery, which is the homogenization localization principle of gamma convergence. Here, there are no constructions. The type of theorems with which you construct this W are very implicit. So there is no explicit construction W. So there is this easy proof of convergence, but difficult proof saying the actual construction of this limit graphon. So I don't want to spend much time, but I just want to say that there is a way, there is a path leading from lattice systems, then understanding that there is something that you cannot describe in lattice systems due to some topological features. There are many gaps in our knowledge of sparse graphs. This can be filled in the case of graphons, but in the case of graphons, the computation of graphons really is what is mysterious to me, at least. So here I will leave these slides. So there is a short reference list, and I thank you for your attention.